Well, welcome. This is a AQA A2 Physcis Unit 4 video. This is now moving on to electromagnetic induction. Now, the first thing I've got over the plan here, as I've begun to do with these kind of videos, I'm going to tell you what we mean by EMF electromagnetic induction and how we induce it in a current. I'm going to tell you how to increase it, how to increase the current that you get. Going to be going on to something called magnetic flux, which is related to the magnetic flux density that we looked at in magnetic fields. I'm going to be introducing something called Faraday's law, which kind of goes off that, and Lenz's law, which them two are very similar, and I'll be explaining why we have the differences that we do. I'm going to go on to talk about EMF in terms of in a fixed coil in a changing magnetic field, and then I'll be just going through some examples and general hints and tips. Now, as I said, this is part 1 of 2. This is the first video. The next video I'll be going on to, I'll be looking at the transformers side of this idea anyway. But the main maths, the main kind of understanding is in this video. In the next video we're just going to be applying that knowledge to transformers. So the first question has to be, what the hell do we mean by electromagnetic induction? Well, electromagnetic induction is just a fancy way, well, it's not a fancy, it's quite complicated for once. I'm actually agreeing with that. So basically what happens is, if we have something like this, say we have a coil, okay, not a good coil, and then we have a magnet, and we put this magnet, obviously with north and south on it, through this coil. Okay, and what happens is we have the magnet which forces the electrons away because of the magnetic field that surrounds this, which is something like that. Okay, and it forces the electrons out of the way. It's a simple way of saying it, really, and it causes them to. Sorry, it creates. The magnet has a permanent magnetic field, and it forces the electrons out of the way, which therefore causes this temporary magnetic field, which is whatever you get when you flow current through a wire, or in this case a coil, and it causes the temporary magnetic field of the or electromagnetic field intersect with the magnetic field of the magnet being put through, which causes this induced EMF. So in short, the magnet goes into the coil, or goes through this other, you could have that in, might not necessarily be a coil, it might be sort of a bar with copper coils wrapped around it, and essentially what you have here is the magnetic field being created by the electrons being moved out of the way, which induces this EMF, and intersection with the permanent magnetic field of the magnet. Obviously these two interact, cause this electromagnetic induction. Okay, so to prove this, a scenario you might have in an experiment you might be expected to do. Okay, so let's come up with two identical coils here. They've got the same number of coils on. It might not draw the same number on. Okay, and we've got two little bits of metal here. Now we know one of them is a magnet, and one of them is just a bit of metal, and we've got to decide which one is which. Now we assume these two are the same size, are made of the same metal, but we need to know which one is the magnet. Okay, so what we would do is we would drop each of these through the copper tube. So as I was saying, we drop these two identical bits of metal through the tube, and whichever one goes the slowest is the one that we assume to be the magnet. Okay, and the reason for that is using this idea that we've established just then. We talked about the electromagnetic induction interacting the magnetic field, and that obviously slows it down because using the magnetic field law for Fleming's left-hand rule, we have a force, and now if that force acted downwards, then we would increase the speed, but because it acts upwards, because essentially this magnet being dropped through provides the the motion, and that's acting downwards, we have the force acting sort of towards the side. So essentially, any way you look at it, the force is slowing the magnet down, okay? And that force is created by this electromagnetic induction, which we talked about just before. So hopefully that makes some kind of sense to you. Okay, so that's electromagnetic induction for you. Or in other words, induced EMF. Okay, so the next thing we're going to look at is how we increase this, how we increase the strength. Now, you could take either one of these two, because essentially these little dashes here represent turns or coils. It's just on a bar magnet, really, essentially, okay? Bar strip of copper, sorry. Okay, so there's a number of things you can do. Obviously, you can either drop this down at a faster rate, because what we're looking at here is an increase in induced EMF. You can either drop it at a fast rate, which will push more electrons, inducing a higher current, or you can have a stronger magnet, which means the magnet will be the magnetic field lines will be stronger, so they'll cut through more of the electromagnetic field lines, which will give you a higher induced EMF. Okay, so as I said, that's a couple of ways that you could do it. Okay, by increasing the strength of the magnet, or by increasing the speed at which the magnet is dropped. Okay, so that's kind of induced EMF. Now we're going to introduce this idea of, there's a lot of introduction happening in this video, but what we're going to look at is, I kind of emphasised that the point about this, something called the magnetic flux density, which we said, well, we got it from F equals BIL, rearrange it to get this B, and we said B is equal to F over IL, okay? And we said that was the magnetic flux density, okay? And that essentially comes, is basically the concentrated field lines. Now, what we're going to go on to look at today is magnetic flux, okay? Now, it's denoted by something that looks like theta, but it's got sort of an I going through a circle, really. And it's equal to the magnetic flux density. Now, magnetic flux and magnetic flux density obviously related, as we're going to show here. But I said that was sort of the concentrated field lines, if you could think of it like that. So if we look at something like this, you know, where you've got the lines, these are the field lines that might be acting on the force of going back to magnetic fields. Okay, but we just look at one of these, and that's the magnetic flux density per unit area. But if we want to look at all of the field lines acting on this plate or this surface, whatever you want to call it, then we have to times it by the area, and that's why we get the magnetic flux. Now, this circle kind of represents the copper, okay, through the induced EMF, so the copper coil, if you wanted to talk about that. Okay, so we need to work out the area, the cross-sectional area. So therefore you times it by A, the area, which gets you the magnetic flux, okay? It's a magnetic flux density times the area. Obviously, the area would be in meters squared, and the magnetic flux density would be in Tesla, okay? So really, that's a new equation, and you would get many questions in the exam from that would require you to be able to work that out. But why do we want to work out, why did we come up with this idea of the magnetic flux? I mean, what's it going to enable us to work out? Well, what physicists like to be able to do is work out things. So we're going to work out the induced EMF. Now, EMF, just to recap, is equation where it is I big R plus I little r, or E is equal to V plus I little r being the internal resistance of the battery. So that's what the EMF is, just to remind yourself. I mean, as I said, we kind of talked about it there, but that was just what this little E represents, okay? And Faraday's law is related to this induced EMF that we see happening from the experiments I've just described, okay? And the actual words it says is the induced EMF is equal to the rate of change of, the induced EMF is proportional to the rate of change of flux through the circuit. Okay, so it's directly proportional. So the EMF is equal to the, the EMF is directly proportional to the rate of change of the magnetic flux. Okay, so it's the rate of change, so delta magnetic flux over delta T, okay? Because that's the rate of change. And then whenever we put a directly proportional, when it's something directly proportional to something else, we put it with a constant of proportionality. So the EMF equals K delta phi, this is what we call this magnetic flux symbol, over delta T. But what does this K represent, okay? So this constant of proportionality, K. What does that represent? Well, the only thing that we change that increases it is the number of turns, which obviously increases the strength of the coil, okay? So therefore, we put is equal to E is equal to N delta phi over delta T. But then we have to introduce something called Faraday's law. Now, Faraday's law, it's Faraday's law. Lenz's law is just that law, except we put a minus in front of the fraction. And that is because in Lenz's law, it says the direction of the induced current, EMF, is such that the current which it causes to the flow of opposite charge from which is producing it. Really, you can just represent that by sort of doing that. And what we've got going down vertically is the current, and we've got the force going through the thumb. Just make sure I've got that right before I just... Yeah, so we've got the current going through the fingers, and then we've got the field, going through the thumb. Okay, so if we want to draw that, your fingers here pointing down, we've got the current, and we've got the field going at right angles to the current. Okay, really that's just using Fleming's left hand rule and ignoring the motion, really, okay? So that makes some kind of sense. Don't know if you can quite see that. But really, it's just using Fleming's left hand rule and ignoring the thumb, okay? Which leads us to say, okay, well, as we're pushing the magnet down here, and the current is going up, if you think of it like that, that's why we put this minus EMF here. Now, if it asks for the magnitude, obviously you would ignore the minus, because the magnitude is sort of like the modulus of it, really, just turns it positive, okay? Right, so that's pretty much most of the information you need to know for this video. Okay, now, just one more thing. We know this is the magnetic flux, this N delta phi, now I said that goes on top because that's the constant proportionality. You may also hear that as asked as the total flux linkage, which is just the total flux times the number of turns. Now, if you were to get a magnet that had no turns, if you were putting through a coil that had no, you would just imagine that it had one. So you would just sort of ignore the N, so to speak. Unless it mentioned it, you would not put it in. Okay, now with all these kind of things, we associate some kind of angle with them, because as I said, it's kind of the force effect. Sure if I've mentioned it yet. So it has to be going at a horizontal, has to be being dropped at a horizontal angle, sort of 90 degrees, perpendicular to the force. But if it's not, you need to make it so. I've got a couple of examples here of what I'm on about. Do apologise. So let me just find the examples and we'll go through it. I can find them in my book. So, because we want it at 90 degrees, you times it by cos theta. So if it's 90 degrees, say cos theta, cos 90 is 1, so if it's at 90 degrees as we want, you just make that, you put cos theta as 1. Sorry about that, it's just kind of emphasising the angle here, okay? So I do apologise about that. I'm just trying to find these questions. Can't seem to find them. Brilliantness. Alright, here they are. Okay, so what I'm going to do is I'm just going to write these questions on the board and then just rub all that rubbish off, and we're going to have a go at them. Sorry, I know some of you may be desperately disappointed that I've not gone ahead and put some questions on there, and that's because I just forgot to do a few variations on that formula that we were talking about for the EMF, the induced EMF, and we said the induced EMF was equal to N phi, being BA, over delta T, okay? Now, we need to know a couple of variations on that equation, and to be able to understand that these are variations, we need to apply it to this principle. Now, what we've got here is we've got electrons flowing along a rod, which is going through a magnet. Now, obviously, because we've got the current flow going vertically, it appears our current finger, which is this second finger, I do apologise, needs to be going from negative to positive. So it needs to be following the electron flow, and if you were to do that with your hand and try and correspond it, then you would get the force going from left to right. Okay, so there's a couple of things we know. Obviously the force is this BIL, and the length of the conductor, which is the electrons are going through, obviously, is length L. Now we know the L in length is measured in distance, which is represented by this little s, okay? So we're going to apply this idea to be able to help us come up with different equations for the EMF. But firstly, we need to recap, well, what was EMF from back in AS physics? Well, we said EMF was the electrical energy per unit charge, okay? So it's little a is equal to big E over Q, okay? So we can also say, therefore, because this is the energy transferred essentially over the charge, therefore we say that's W over Q, okay? Means the same thing as E over Q, which is also the EMF. Now the induced EMF and the EMF mean the same thing. Obviously, the induced EMF is just caused by a different method. It's still EMF, but we just call it induced because of the way it's created. Okay, now we know the work done. Okay, so let's go from this equation, the E is equal to W over Q. Now all these different steps are one magnitude of different equations that we're going to be going through. So just make sure I've... Okay, right, no, that's nothing important, they can wait. Okay, so E is equal to W over Q, and W we said was force times distance, or Fs, okay? That was over Q. Now we know the force is BIL, so therefore the EMF is equal to F times, the BIL, which is F times S, so BILS, or bills, B, over the charge, okay? And we know the charge is Q equals IT, so therefore the EMF is equal to BILS over IT, which means these two i's cancel, therefore the EMF is equal to BLS over T. Okay, so that's one equation there that you could use. Sorry, this is, just rewrite that again because that wasn't very good. BLS over delta T. Okay, so these are all different equations that you could use for the EMF. So you can see there's a variance there. There's quite a big number. And now we know the area. Well, there's a couple of formulas we've got for area, which is length. We can say the area is a length times the distance, even though that kind of means the same thing. Okay, so we can replace this length and distance with the area. So therefore E is equal to BA over T. So therefore, as we know, BA equals phi, therefore E is equal to E is equal to phi over delta T. Okay, so that's another equation. Now, if you don't understand that last little step, I've got another equation, another way of thinking of it. That's a hell of a lot simpler. In my mind, anyway. You can just simply sub in what phi is in this equation. N is equal to phi over delta T. And we know phi is BA, so it equals, this N is 1 because we've only got one sort of thing here, so it just equals phi over delta T. Okay? So that's just one way you can work it out. As I said, the reason we did all that was because we are moving across the distance, which means we have to include the force and the distance, and that's why we do that work done transferred. But in the end, we just got to the original equation, okay, which obviously we should do. Now I've got another method that if you want me to go through, it's a lot longer, but you get the same answer. It's just another way of looking at it, but I think that way there is the most simple. Okay, so that, as I said, that's just something I missed out. But obviously, I realised that when I came to do the next part of the equation. Now, I'm not sure if I mentioned this, but okay, so this phi, well, we obviously measure it in the angles as well, because it has to be perpendicular to obey the law. We don't really generally refer to this, but it's the BA, and we times that by the cos theta. Okay, and obviously cos theta is always 90 degrees for this when we're talking about this. So cos 90 equals 1, so it's just theta equals BA. But really, we've got this cos theta as well. Okay, and then you just apply n to both sides, times both sides by n to get the number of turns. Okay, well, as I said, that's just something else if you wanted to go on and talk about that. Right, so what we're going to go on to now is just a few examples really about this idea of including the angle, because we've mentioned this angle thing, but now, you know, we need to apply it to be able to actually understand what it means. So we've got a few scenarios here that just kind of emphasise this. Do apologise. Okay, so each one of these bars has a length of 8 centimetres. Now I'm going to write it on the first one, but I can't bother writing it on every single one. So they've all got a length of 8 centimetres. Okay, and this one is moving horizontally at a speed of 3 metres per second. Okay, so that's part A. And what he wants us to work out is the direction and the magnitude of the induced EMF in each case. Well, we know the EMF is equal to the number of turns, n, which for all of them is 1, so we can kind of ignore that, times phi, over delta t. Sorry about that. I mean, I'm not sure where I'm going to edit my complete mess out, but okay, so we know the area of this particular, so this is an example really of a rod that is moving through causing electromagnetic induction. Okay, when it's moving through an area, we need to figure out kind of what area is it moving through, and we know it's the length L delta S. Okay, so we sub that into this equation. So B is equal to B times L delta S over delta T. I know, yeah, length times distance, which is weird, but we'll just go with it. Okay, so when we do this equation, so BL, so magnetic flux density times the length times the distance over the time. Okay, well, when we do the, basically you think of this as, yeah, so times is on the top, so B times L times delta S over delta T. Delta S and the delta T, well, V equals delta S over delta T, so delta is changing, obviously, so therefore the EMF is equal to BLV. I know it's not a very good explanation, but we'll just arrive at that. As I said, if you want to have a go at a stab and explain that in the comments, please do. Don't think I've done a very good job at it. If you want to do it for the benefit of other people, obviously, I know what I'm talking about, obviously, you know, that's completely fine. But this is the main equation we're going to be using for questions like this, okay? So, just add a few in there. Okay, so we've got that one. Just get the few of those up. I had them as well. Okay, there we are. Sorry about this. Okay, so then we've got, as I said, they're all 8 centimetres. This one is travelling at 60 degrees to the horizontal. That's 3 metres per second. And the third one, call this bit C, okay, has been pulled at 60 degrees, 3 metres per second. Okay, so we need to work out the EMF for each of these. Now, we're obviously going to use this equation, okay? So the first one's nice and simple. It's already at right angles, so we don't need to do anything else with it. Okay, sorry, you add on at the end here cos theta, because we need to sort of sacrifice, you know, basic trigonometry. Okay, so the first one is at right angles, so it's just going to be cos 90, which is 1. So therefore, the EMF for A is equal to B times L times V times cos theta. And we're told the magnetic flux density is 4 times 10 to the minus 2 in each case. Okay, so the B, or the beta, is equal to 4 times 10 to the minus 2. Okay, Tesla, sorry. Okay, so it's just a case of subbing that into this equation using the relevant, the length and the velocity. However, because this is in centimetres, this is in metres per second, we need to convert that to metres. Now, you should know there's 100 centimetres in a metre, so we just divide it by 100, okay? So the EMF is equal to E, is equal to 4 times 10 to the minus 2 times the length, which is 8 times 10 to the minus 2. Sorry, I'm pretty sure that's the wrong input. Yeah, no it's not. Don't know why I thought that was wrong. Yeah, 8 times 10 to the minus 2 times the velocity, which is 3 meters per second, times cos of 90, which is obviously 1. We'll put it in anyway just to get used to it. Okay, and if you sub that in your calculator, you should get a value of 9.86 times 10 to the 3 volts, because it's measured in volts, remember, EMF. Okay, apply the same logic to the other two, and for this one you need to include the angle because it's moving at the angle. Okay, so if you were to do that, it'd be E is equal to 4.4 times 10 to the minus 2 times 8 times 10 to the minus 2 times 3 meters per second times the cos of 60. And you'd get a value for that of 8.3 times 10 to the 3. Minus 3, sorry. Okay, now this part C, because it's just being pulled at that angle, it's not actually moving at that angle, you would get the same answer as for part A, which is this 9.86 times 10 to the minus 3. Okay, so as I said, hopefully that kind of explained it. I do apologise, it's not been the most advanced explanation. But what we're just going to go on to now is just a couple of graphs, really, just to finish this topic off. And the graphs we're going to look at is flux linkage and induced EMF against time. Okay, so draw yourself 2 axes on your graph, on your table, sheet paper. Do apologise. And they're both going to have a x-axis of time, and one's going to have flux linkage, and the other is going to have induced EMF. An induced EMF just has a horizontal line, whereas a flux linkage has a constant gradient. Now, why is that? Well, the induced EMF, well, you don't alter the rate, the EMF. It's just, it's at a set level, and that's because obviously when the north passes through, if you imagine in magnets dropping it through the coil, then yeah, when the coil, sorry, one sec. Yeah, because if we're dropping it through that coil, then obviously the north goes through and the south goes through, and it is either on or off. Okay, this EMF, but this flux linkage, so when the north loses, the EMF, the south gains it up, and there's no loss in EMF, if you can imagine it as that. Okay, so the flux linkage, well, we said the flux linkage, the total flux linkage, is N equal N phi, which is NBA, which is not the American spot, just NBA. Well, the flux linkage, okay, well, N obviously stays the same, B stays the same, the area stays the same, but because this is the flux linkage against time, it's at a constant gradient because we're constantly increasing. This is for different flux linkages. Okay, so basically that it's not. Yeah. So this would be like, you know, a 1 flux linkage, a 2, a 3. When you increase the flux linkage, you have to increase the number of turns because the flux density in the area stay the same, you assume. So that's why you get this constant of proportionality, which we said was the N. Okay. And then in this, as I said, you know, it's just one. It's either on or off. You don't get a different level of induced EMF. Okay. So hopefully, as I said, that tried to explain some of it. Okay. Right. So hopefully that made some kind of sense to you. Now, that's pretty much it for part 1. Really, it's just about, just recapping, it's just using that equation, understanding what induced EMF is, Lenz's law, Faraday's law, which just combine to give the equation. Remember, Faraday's law is the actual equation for induced EMF, which is N BA or phi over T, delta T. And Lenz's law just puts a minus sign there, and that's just because of the way you're looking at it. It'd be this hand, wouldn't it? So it'd be going that way. So it's just your right hand, and your fingers down are your current, and your finger across is your field. Okay, so it's just really, as I said, it's a variation of Fleming's left hand rule. Okay, and you just evolve that delta T to, you know, if you were working, you would find out that delta T if you were moving something across. If you were moving a magnet across an electromagnetic field, then you would just work out D by, obviously, the speed over the distance. If you needed to work out delta T, but obviously you knew that. Okay, so really it's just a case of applying all we've done today in terms of the equations, but subbing it in and understanding how we induce it, which is just when you drop a magnet through a coil, the permanent magnetic field of the magnet intersects with the temporary magnetic field of, because when you drop a magnet through, you push the electrons away, which causes the induced EMF, which produces a temporary electromagnetic current, which intersects the magnetic current of the field, the magnet, which obviously causes these forces. And as I said at the beginning, with them 2 tubes that are demonstrated on the board, it slows it down because we've got, obviously, it's almost like a resistance force, essentially. Okay, so that's kind of an overview of this induced EMF. Okay. So I do apologise, it's not been the most slickest of videos, and I'm trying to get back up to how slick they used to be, and I'm not going to keep results of the books. But you know, I will do another video if you find it too putty-offery, if that makes sense. But as I said, most of the information I've kind of thrown at you, and hopefully I'll edit out all my mistakes, but I'll still, you know, leave a few just for comical effect, and make sure you're actually paying attention. Okay, so thanks for watching, and we'll see you in the next video. That probably right.